Yes, sir.
So after that we shall discuss today. We shall discuss your yesterday we have also discussed orthogonal matrix and unitary matrix A dagger is equal to A inverse. Your A is a real matrix, then A dagger is equal to A transpose star is equal to A transpose. Therefore, real and unitary matrix and is defined by A inverse. And this is the condition for orthogonality. Your A transpose is equal to A inverse. If this equation is satisfied, then it will call it is orthogonal. Similarly, Hermitian matrix, which is very much important in quantum mechanics to realize whether it is a physical entity or not. And if your matrix A is labeled Hermitian, if your A is equal to A dagger. So self-adjoint property, if it will be proved, then it will be Hermitian matrix, where A is real and is a physical object. So A dagger is equal to A transpose. So real Hermitian matrix are all real symmetry matrix. And your P is not equal to P dagger, it is called non-Hermitian matrix. And here is an example. You can see here A star is equal to 0 I minus I0 Pauli matrix. A transpose is equal to A transpose is equal to 0 minus I0. So A dagger is equal to A. So it is Hermitian. Similarly, if A and B are two non-commutating Hermitian matrices, you can see AB minus BA is equal to IC and your C is Hermitian. So A dagger is equal to A, B dagger is equal to B, C is equal to minus I AB minus BA. So your C dagger will be minus I AB minus BA. So the C dagger is equal to C, so it is Hermitian. Then you can solve a system of linear equations by matrix method. And this is the method and very useful in solving a system of linear equations. So let us consider a system of linear equations. A11 x1, A12 x2 plus so on so forth. A1n x1 is equal to B1 and an1 x1 plus an2 x2 plus so on so forth. Ann x1 is equal to Bn. So what you have to do now? First rearrange them. A11, A12, so on so forth. A1x, A21, A22, so on so forth. A2x will be organized in a matrix. Similarly, the column matrix x1, x2, so on and so forth, xn will be placed there, and this is nothing but B1, B2, so on and so forth, Bn in a column matrix. So you can write Ax is equal to B, or A matrix is equal to A11, A12, so on and so forth, Ax, and your X matrix is the column matrix X1, X2, so on and so forth, Xn, and capital B is equal to the column matrix small b1, small b2, so on and so forth, Bn. So what you will have to do, your A, X, and B can be written like this, and at the N cross N matrix, A is called the coefficient matrix of the system. So X is a N cross 1 column matrix or column vector, and B is a N cross 1 column matrix or column vector. So we assume that the coefficient matrix A and the column matrix B are all known. There are different solutions depending on the rank of the matrix A. So let us consider three different cases. In case 1, B is not equal to 0, and determinant of A is not equal to 0 here. So here the matrix A is non-singular, so you have A inverse. So since A inverse exists, let multiplying equation 1.25, this equation 1.25 by A inverse, you will get A inverse Ax is equal to A inverse B. So your X is equal to A inverse Ax, which is nothing but A inverse B, and your A inverse will be evaluated from the formula adjoint of A divided by determinant of A. So X is equal to adjoint of A multiplied by B divided by determinant of A. So by Cramer's rule, you can have your Xi is equal to 1 by determinant of A multiplied by B1 A 1i plus B2 A 2i, so on and so forth, where I is equal to 1 to so on and so forth A. And in case 2, B is equal to 0 and determinant of A is not equal to 0. Case 1, your B is not equal to 0, determinant of A is not equal to 0. Case 2, B is equal to 0, determinant of A is not equal to 0. So in this case, the equations are homogeneous and you have Ax is equal to 0. Since B is equal to 0, the system has a unique solution, and the x1 is equal to x2 is equal to x3, so on and so forth is equal to xn is equal to 0. And this unique solution is called trivial solution. And in the third case, nothing is 0. So nothing is non-zero. Your B is equal to 0 and the determinant of A is equal to 0. So your A is a circular matrix and the system has a large number of non-zero and non-trivial solutions. Let us have an example so that you can have a better feel how to solve a system of linear equations. X1 plus 2x2 plus 3x3 is equal to 8. 2x1 plus 3x2 minus 4x3 is equal to 5. 3x1 minus x2 plus 2x3 is equal to 10. So this set of equations can be written in the matrix form 1, 2, 3, 2, 3 minus 4, 3 minus 1, 2. This is nothing but coefficients of x1, x2 and x3 in the system of linear equations. And you can write in a column matrix x1, x2, x3. And your B can be written as the right hand side of the equation, that is 8, 5 and 10. So it is arranged in a matrix form Ax is equal to B. Where A is equal to 1, 2, 3, 2, 3 minus 1, 3 minus 1, 2. And your X is equal to x1, x2, x3, and B is equal to 8, 5, 10. So what we will have to do, your A, X and B is written in a matrix form, and your, determinant of A, if you evaluate here, it is 63, and it is non-zero. So your A inverse will exist. So your X is equal to A inverse B, that is the adjoint of AB by determinant of A. So by using the Cramer rule, your Xi is equal to 1 by determinant of A all multiplied by B1 A 1i plus B2 A 2i plus B3 A 3i, where I is equal to 1 to 3. So A 1i is the cofactor of the element A1i, small a 1i, smallest subscript 1i. So your A11 can be written as your determinant will be determinant multiplied by the factor. So your A11 is equal to how much? A11 is equal to minus 1 to the power 1 plus 1 multiplied by 2 is equal to 2. So the cofactor of the A11 that is equal to 2. Similarly, A21 is equal to minus 17 and A13 is equal to minus 11. A11 is equal to 2, A21 is equal to minus 7, A31 is equal to minus 17, A13 is equal to minus 11, A23 is equal to 7, A33 is equal to minus 1. And arrange these two things in the format shown in the expression. So your x1 is equal to 1 by determinant of A multiplied by B1 A1i plus B2 A2i B1 plus A11 plus B2 A21 plus B3 A31. So if you put the values, that is 16 minus 35 minus 170, you will have your 1 by 63 multiplied by 16 minus 35 minus 170 is equal to 3. So x1 is equal to 3. Similarly, x2 will be 1 and x3 will be 1. Similarly, you can solve the equations and get the unknown in the equation, that is x1, x2 and x3. So what is the rank of the matrix, which I have discussed earlier in this class? The rank of the matrix is the largest of the orders of all non-zero minors of that matrix. So it is denoted by A, where A is the matrix S. So if A is a n cross n matrix, the rank of the matrix is R. If and only if there exists at least one non-zero minor of capital A of the order n, and every minor of A of higher order R plus 1, R plus 2 is 0. In other words, you can say the rank of the matrix A is the maximum number of linearly independent row vectors of A. So it is denoted by the rank of A. So let us have an example so that we can have a little feel. The matrix is A, and A can be written as 3022 minus 642 24 54 21 minus 21 0 minus 15. So the given value is this. Now you add row 2 with it, 2 multiplied by row 1 and row 3 minus 7 row 1, and you will have 3022 0 42 28 58 0 minus 21 minus 14 minus 29. In the next step, you in the third row, you change this row 3 plus half row 2, and the third row will become 0 0 2 2, and now it cannot be further. It can not further simplified, and non-zero values are only in 1 2 rows. The rank is 2. There are two theorems. Row equivalent matrices have the same rank. P vectors with n components each are linearly independent. If the matrix with these vectors as row vectors has rank P, but they are linearly dependent if that rank is less than 2. And theorem 3, the rank R of a matrix A equals the maximum number of linearly independent column vector A. So A and its transpose A superscript T have the same rank. And you can remember these things. Rank B transpose A transpose is equal to the rank of AB. Rank A is equal to rank B does not imply that rank A square is equal to rank B square. Rank of a product of matrix cannot exceed the rank of either factor. Okay. So, and you can also solve equations, system of equations using gap substitution, which is discovered by Gauss, the great mathematician, and it is also called Gauss elimination. And it is a standard elimination method for solving linear systems, but proceeds symmetrically irrespective of particular features of the coefficients. It is a method of great practical importance and is reasonable with respect to computing time and storage demand. So, let us begin by motivating the method. The system is in a triangular form. 2x1, 5x2 is equal to 2, and 13x3 is equal to minus 20. You see, it is in triangular form. You can solve it by back substitution. That is, solve the last equation for the variable x2. So, look here in the second equation, the last equation in the triangle, there is one unknown. That is x2. 13x2 is equal to minus 26. So, unknown is only x2. So, you can have the value of x2 by putting this equation. 13x2 is equal to minus 26, and the x2 will be minus 26 by 13 is equal to minus 2. Now, put this value minus 2 in the first equation in place of x2, and you will have your x1 is equal to half multiplied by 2 minus 5x2, that is half multiplied by 2 minus minus 10, which is nothing but 12 by 2 is equal to 6. Instead of the idea, first reducing the general system to triangular form and then solve it. And here your 2x1 plus 5x2 minus 2 minus 4x1 plus 3x2 is equal to minus 30. It is not in a triangular form. So you have to make it in triangular form. After that, you can have the back substitution. So how to make it in triangular form? Let us have the augmented matrix, that is the coefficients of the unknowns and the value of the right hand side. So that is 2, 5, 2 minus 4, 3 minus 30. So this is not in triangular form, but we can make it. So we leave the first equation as if, and we eliminate x1 from the second equation to get a triangular system. For this, we add twice the first equation to the second. 2 multiplied by 2x1 plus 5x2 is equal to 2 is twice the first equation, and we add this with minus 4x1 plus 3x2 is equal to 30 minus 30. So you can see the first equation will become 4x1 plus 10x2 is equal to 4, and in the second equation minus 4x1 plus 3x2 is equal to minus 30. So the second row will be transformed like this, and you will have your 13x2 is equal to minus 26 as minus 4x1 and plus 4x1 will cancel out, and your 10x2 plus 3x2 is equal to 13x2, and 4 plus minus 30 is equal to minus 26. Now you can arrange it in a matrix form, and you will have 2, 5, 2, 0, 13 minus 26. It is the triangular form of the matrix. So here you can see that 13x2 is equal to minus 26. And we have 2x1 plus 5 into minus 2 is equal to minus 10 is equal to 2. 2 minus plus 10 is equal to 12. So your 2x1 is equal to 12 and x1 is equal to 12 by 2 is equal to 6. So it is solved. Similarly, by the back substitution, cross elimination, we can solve a system of equations having a more than n number of rows and n number of columns. The voice is fluctuating. Is it audible now?
No, sir.
I am not audible. I am not audible.
Sir, your voice is fluctuating.
Check this. Am I audible? Am I audible? Okay. So let us try another way. Am I audible now? Am I audible?
Yes, sir.
Yeah, it's clear, sir.
Okay. So let us continue. So we can have also Gauss elimination or partial pivoting of to solve the system. 8x2 plus 2x3 is equal to minus 7. 3x1 plus 5x2 is equal to plus 2x3 is equal to 8. And 6x1 plus 2x2 plus 8x3 is equal to 26. So let us have the augmented matrix. That is nothing but 6, 28, 26, 3, 5, 6, 2, 8, 26, 3, 5, 2, 8, 0, 8, 2, minus 7. Now eliminate minus 3x1 and you will have minus 3. Eliminate 3 in the 3x1. So you will have, how can you get it? by subtracting 3 by 6 is equal to half times the pivot equation from the second equation. So the matrix will become 6, 2, 8, 26, 0, 4, minus 2, minus 5, 0, 8, 2, minus 7. Now in the step to eliminate x2, how can you eliminate x2? By interchanging the equation 2 and 3. So you will have 6, 2, 8, 26, 0, 8, 2, minus 7, 0, 4, minus 2, minus 5. Just interchange row 2 and row 3 among themselves. Then eliminate your x2 from the third equation. For this, you subtract half time the pivot equation from the third equation. And the resulting triangular system is 6, 2, 8, 26, 0, 8, 2, minus 7, 0, 0, minus 3 by 2. Now it is in triangular form. So the last equation is minus 3x3 is equal to minus 3 by 2. So your x3 is equal to a half. By putting the value of x3 in the second equation, you will have your x2 is equal to minus 1. And by putting the value of x2 is equal to minus 1 and x3 is equal to half in the first equation, you have your x1 is equal to 4. Similarly, you can solve linear equations as shown in the screen. X1 minus x2 plus x3 is equal to 0, minus x1 plus x2 minus x3 is equal to 0, n x2 plus 25x3 is equal to 90, 20x1 plus 10x2 is equal to 80. Okay, so you eliminate the row, the elements in the row and make it in triangular form, and you can solve it. So this is the triangular form matrix. Okay, so first you will have your minus 95, x3 is equal to 190. From that, you will have your x3 is equal to 2, matrix A. And by putting the value of x3 in the second equation, you will have x2 is equal to 1 by 10 multiplied by 90 minus 25 x3, and your x1 is equal to x2 minus x3. So the solution is unique here. Similarly, Gauss elimination of infinitely many solutions. It's a Gauss elimination if infinitely many solutions exist as shown in the example. So this is the solution. You can see. And you can see here that x1 is equal to 2 minus x4 is equal to 2 minus t2, and x2 is equal to 1 minus x3 plus 4x4 is equal to 1 minus t. Your x3 is equal to t1 and x4 is equal to t2. Then Gauss elimination of where no solution exists. So this is the thing. The false statement 0 is equal to 12 shows that the system has no solution. Because in here you can have your 0 is equal to 12, which is not possible. So it has 0 solution. Then your elementary transformation. Any one of the following operation on n matrix is called an elementary transformation. You can do this by interchanging any two rows or columns. This transformation is indicated by Rij. If the ith and jth rows are interchanged, multiplication of the element of any row or column by a non-zero scalar quantity to get Krj, addition of constant multiplication of the element of any row to the corresponding element of any other row, Ri plus Krj. There is an example you can see. It is the following matrix to upper triangular form, echelon form. Please mute. Please mute. Okay. Then the elementary matrices I is equal to 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. Then you can compute the inverse of the matrix form of the elementary matrix by Gauss-Jordan method. So if A is reduced to I by elementary transformation, your PA is equal to I, where P is equal to Pn, Pn minus 1. So both P was the matrix of
Auntie.
This requires that the transformation occurs in pairs. So use Gauss-Jordan reduction method to compute the inverse of the matrix. P minus 3, 4, 2 minus 3, 4, 0 minus 1 1 by applying elementary row transformation. The solution is shown in the screen. You can have it. N minus 2 similarly you can the inverse of minus 2 minus 6 minus 3 minus 13 minus 4 minus 7 minus 1. Okay. Then
Voice is fluctuating.
minus 2 1 0 1 1 0 2 minus 1 minus 4 1 minus 3 1 minus of 0 minus 2 2. Similarly, there are some more examples. Please mute yourself. You are
आंटी
disturbing other
ମୁଁ
people.
ଜଲ୍ଦି ପଳଉଛି ମ
You are disturbing other people. For the admin, please mute those
ମାରି
people who are
ପକେଇଲେ
disturbing
ପଳଉଛି
or
ସେତେ
creating noise. Admin, please mute. Those are being unmuted.
ସେଇଟା ମାରିଦେବି
Am I audible? Am I audible? Please mute.
ଆରେ ମ୍ୟୁଟ କର କିଏ ସେ ମ୍ୟୁଟ କର ଟିକେ ଶୁଣା ଯାଉନି କିଛି।
Okay, I think those students are mute themselves. So next is Gram-Schmidt procedure. So in an n-dimensional vector space with an inner or scalar product, we can always construct an orthonormal basis of n vectors, that is W1 vector with W1 vector dot product Wj vector is equal to del ij Kroneker's delta, starting from a n linear independent vectors Vi, where I is equal to 0, 1, so on and so forth, n minus 1. So we start by normalizing V0 to unity, and we can define it omega 0 vector is equal to V0 vector by root over of V0 square. V0 square. Then we project V0 vector from V1 vector, forming U1 vector is equal to V1 vector plus A10 omega 0 vector with the admixture coefficient A10 chosen so that V0 vector dot product U1 vector is equal to 0. Dotting V0 vector into U1 vector yields A10 is equal to minus V0 dot V1 divided by root over of V0 vector is equal to minus V1 vector dot product W0 vector. Am I audible? Am I audible?
Yes, sir.
Okay. So your uj vector can be written as vj vector plus aj0 w0 vector plus aj1 w1 vector plus so on and so forth ajj minus 1 wj vector minus 1 wj minus 1 vector with the coefficients aji is equal to minus vj dot wi vector. So wj vector is equal to uj vector by root over of uj square completes our construction. And you can see this Gram-Schmidt procedure is one possible way of constructing an orthonormal, orthogonal or orthonormal set. The vector wi are not unique. There is an infinite number of possible orthonormal sets. So the freedom involved, consider two non-parallel vectors A and B in the xy plane. So we may normalize A to unit magnitude and then form B dash vector is equal to A small a capital A vector plus B vector, so that B dash vector is perpendicular to A vector. So by normalizing B vector, we have completed the Gram-Schmidt orthonormalization for two vectors. But any two perpendicular unit vectors such as u cap and y cap could have been chosen as our orthonormal set. Again, with an infinite number of possible rotation of x cap and y cap about the z axis, we have an infinite number of possible orthonormal sets. So your vector by Gram-Schmidt orthonormalization, to illustrate the method, we can consider two vector, v0 vector is equal to 1, 1 and v1 vector is equal to 1, minus 2. So these are neither orthogonal nor normalized. So normalizing the first vector, w0 vector is equal to v0 vector by root over of 2. We then construct u1 vector is equal to v1 vector plus a small a subscript 1, 0 or w0 vector so as to be orthogonal to v0 vector. So this yields ui vector dot v0 vector is equal to 0, which is equal to v1 vector dot v0 vector plus a10 by root over of 2 all multiplied by v0 vector square is equal to minus 1 plus a10 v2. So the adjustable admixture coefficient a10 is equal to 1 by root 2. As a result, v1 vector is equal to your matrix A1 minus 2 plus half O matrix 1, 1. This is nothing but 3, 2 multiplied by matrix 1 minus 1. So your W1 vector is equal to 1 by root 2, 1 minus 1 matrix. So you can check that W0 vector dot Wj vector is equal to 0. And these two vectors W0 and W1 form an orthonormal set of vectors, a basis of two-dimensional Euclidean space.
हेलो।
जी सर बताइए, मनोज जी।
हाँ सर, मैं बोल रहा था कि सर थोड़ा लेक्चर बहुत फास्ट हो जा रहे हैं सर, समझ में नहीं आ रहे।
अरे भाई,
थोड़ा सा अगर स्लो
आपके
से तो।
क्लास में आपका 4 क्रेडिट का कोर्स पढ़ाना है। 4 क्रेडिट के कोर्स के लिए 60 आवर अलॉटेड होता है नॉर्मल यूनिवर्सिटी कॉलेज में। 60 को आप 4 में जैसे पढ़ाओगे या 8 में तो फास्ट होगा ही। हम क्या कर सकते हैं, you have to arrange 60 classes for a normal 4 credit course in a college or university, or at least 40 classes. Here it is counseling only. There is no class system, I think. So they have only allotted 4 days and 8 classes. So you can also think about it, and it is very difficult to complete around 1,000. How much it is? This course material is block 2. Block 2 is your around. Block 2 is around how much? How many pages? This is around 100 pages. So at least 500 pages of material. 114 pages. Block 2. Similarly, 4 material, if you will consider, it will be around 600 pages. 600 pages, 8 hours. And it is mathematics. Mathematical physics, not mathematics. Physics having a mathematical flavor. So you can realize also it is very difficult, and it is since it is very difficult, they have not give a nomenclature class. I think they have given the nomenclature counseling. So I will give you an basic idea, and you will give through the material, I think, and you will prepare for your exam. Manoj ji?
Okay, sir.
So I think like that, and if they will give justice to the course, they have to give at least 40 to 60 classes, so that they can have a blackboard like teaching in the notepad, or having some other method where we can have a slow motion. Am I clear?
Okay, sir. Thank you, sir.
This is a counseling class, I think. So it will obviously be fast. So you can go through your course material, Mathematical Physics 2, Block 2, and you will realize. And before that, each class also, you can have a overlook over the material, so that you will better understand. Okay. Manoj ji?
Yes, sir.
Okay, thank you. Then Gram-Schmidt orthogonalization. Gram-Schmidt orthogonalization is a method that takes a non-orthogonal set of linearly independent vectors or functions and construct an orthogonal set of vectors or functions over an arbitrary interval and with respect to an arbitrary weight or density factor. In the language of linear algebra, the process is equivalent to a matrix transformation relating an orthogonal set of basic vectors to an orthogonal set. So you can apply the Gram-Schmidt procedure to a set of functions, and the functions involved may be real or complex. And for convenience, they are assumed to be real. And the generalization to the complex case often offers no difficulty. So before taking up orthogonalization, we should consider normalization of functions. So no normalization has been specified. So your integration over a to b phi I square omega dx is equal to your ni. But no attention has been paid to the value ni. Since our basic equation is linear and homogeneous, and we may multiply our solution by any constant, and it will still be a solution. We now demand that each solution qi be multiplied by ni inverse, so that nu phi I will satisfy integration a to b phi I square omega dx is equal to 1, where phi I is a function of x and omega is a function of x. And your integration a to b phi I phi j omega dx is equal to del ij, where del ij is the Kroneker's delta. It can only two values, 0 or 1, depending upon the value of I and j. And equation your 1.36, that is integration a to b phi I square omega dx is equal to 1, says that we have normalized two units, including the property of orthogonality. So functions satisfying this equation are said to be orthonormal. That is orthogonal plus unit normalization. Other normalizations are content certainly possible, and indeed by historical convention, each of the special functions of mathematical physics will be normalized differently. So we can consider three sets of functions: an original linearly independent given set un, which is a function of x, where n is equal to 0, 1, 2, so on and so forth. An orthogonalized set psi n to be constructed and a final set of functions phi n which are the normalized psi n. So you can see your un which is a function of x, psi n which is a function of x, and phi n which is a function of x. Your un is linearly independent, non-orthogonal, and on-normalized. Psi n is linearly independent, orthogonal, and on-normalized. Phi n is equal to linearly independent, orthogonal, and normalized, that is orthonormal. And your Gram-Schmidt procedure takes the nth psi function to be un plus an unknown linear combination of the previous phi. The presence of the new un will guarantee linear independence. The requirement that psi n be orthogonal to each of the previous phi yields just enough constants to determine each of the unknown coefficients. So fully determined psi n will be normalized to unit yielding phi n, and your sequence of step is repeated for psi n plus 1 which is a function of x. So we can start with n is equal to 0 and your psi 0 which is a function of x is nothing but u0 which is a function of x with no previous phi to worry about. Then we can normalize phi 0 which is a function of x by using the formula psi 0 divided by integration psi 0 square omega dx to the power half. And for n is equal to 1, let us you have n is equal to 1, so your psi 1 is equal to u1 plus a1050, and psi 1 be orthogonal to phi 0. So at this stage the normalization of psi 1 is irrelevant, and orthogonality leads to integration psi 1 psi 0 omega dx, which is nothing but integration of u1 phi 0 omega dx plus a10 integration phi 0 square omega dx is equal to 0. So phi 0 is normalized to unit, and we have a1 comma 0 is equal to minus integration u1 phi 0 omega dx. So fixing the value of a10 normalizing, we define phi 1 is equal to psi 1 divided by integration psi 1 square omega dx to the power half, and we generalize it so that phi I is equal to psi I divided by integration psi I square omega dx to the power half, and your psi I is equal to ui plus a subscript I comma 0 phi 0 is equal to a I1 phi 1 so on so forth. And the coefficients a I j are given by minus integration ui phi j omega dx. So if some other normalization is selected, you can have your integration a to b phi j square omega dx is equal to mj square, and this can be replaced by phi I is equal to ni psi I integration psi I square omega dx to the power half, and your aij is equal to minus integration ui phi j omega dx is equal by nj capital N subscript j square. So this can be rewritten in terms of projection operator Pj, and we consider the phi n to form a linear vector space. Then the integral may be interpreted as a projection of ui into the phi j coordinate or the jth component of ui, with Pj ui is equal to integration ui phi j omega dt multiplied by phi j. So your psi I will become 1 minus summation j is equal j is equal to 1 to I minus 1 projection operator Pj ui. So subtracting the components j is equal to 1 to I minus 1 leaves psi I orthogonal to all the phi j. It will be noticed that although this Gram-Schmidt procedure is one possible way of constructing an orthogonal or orthonormal set, the functions phi I are not unique. There is an infinite number of possible orthonormal sets for a given interval and a given density function. As an illustration of the freedom involved, consider two non-parallel vectors A and B in xy plane. So you may normalize A to unit magnitude and then form B vector is equal to small a multiplied by capital A vector plus capital B vector, so that B dash is perpendicular to A vector. By normalizing B dash vector, we have completed the Gram-Schmidt orthogonalization for two vectors. But any two perpendicular unit vectors such as x cap and y cap would have been chosen as our orthonormal set. Again, with an infinite number of possible rotation of x cap and y cap about z axis, we have an infinite number of possible orthonormal sets. So let us have an example. Legendre polynomial you know in your BSc class, and you can have it by Gram-Schmidt orthogonalization. It is shown in the screen. So your un is equal to x to the power n, where n is equal to 0, 1, 2, and the interval is minus 1, smaller equal to x, smaller equal to 1. So your omega vector, omega is equal to 1. So by Gram-Schmidt orthogonalization, your u0 is equal to 1, phi 0 is equal to 1 by root 2, and psi 1 is equal to x plus a10 multiplied by 1 by root over 2, and where a10 is equal to minus integration minus 1 to 1 x by root over 2 dx is equal to 0. So by symmetry, you can write psi 1 is normalized to be obtained. Phi 1 is equal to root over of 3 by 2x. Then we continue to Gram-Schmidt procedure with psi 2 is equal to x square plus a20 into 1 by root over of 2 plus a21 root over of 3 by 2x, where a20 is equal to minus root 2 by 3, and your a21 is equal to 0, and your psi 2 is equal to x square minus 1 by 3. So normalizing to unity, your phi 2 is equal to root over of 5 by 2 into 1 by 2 multiplied by 3x square minus 1. And your next function, phi 3 becomes, phi 3 is equal to root over of 7 by 2 multiplied by half, whole multiplied by 5x square minus 3x. And your phi n, which is a function of x, can be written as root over of 2n plus 1 divided by 2 pnx, where pn is the nth order Legendre polynomial. So you can see Gram-Schmidt process provides possible but very cumbersome method of generating the Legendre polynomial. So a power series expansion in un is equal to x to the power n is not orthogonal, can be converted into an orthogonal series. So here is the it is represented in a tabular form: Legendre, shifted Legendre, Chebyshev 1, shifted Chebyshev 1, Chebyshev 2, Laguri, set Laguri and Hermite. And your interval weighting function standard normalization is written in a tabular form. Here you can see in the screen. Am I audible?
Yes, sir.
Okay. Then we can go further. It is also very much important in quantum mechanics, eigenvalues and eigenvectors. You can see q cap psi is equal to small q psi, and q cap small q ket is equal to q small q ket. So q cap is an operator and q are scalar. So psi is called eigen function here. Psi is called eigen function. Q cap is called operator. Eigen when an operator is operated upon a eigen function, it will give eigen value multiplied by that function. So here small q is the eigen value. So ket q is the eigenvector of q cap belonging to the eigenvalue q. These equations are called eigenvalue equations. Q cap psi is equal to q psi is an eigenvalue equation. In quantum mechanics, we represent operators by matrix, and matrix form of an eigenvalue equation is Ax is equal to lambda x. Ax is the eigenvector of the matrix A belong to the eigenvalue lambda. So you can write Ax is equal to lambda Ex, where I is the identity. So in the previous, in today's class, earlier in the today's class, we have Pauli matrix, and this is a part of quantum mechanics. So quantum mechanical problem can be solved by using matrix algebra or matrix formalism. So your Ax is equal to lambda Ix, and your A minus lambda I multiplied by Ax is equal to 0. So you know that the necessary condition for the non-trivial solution Bx is equal to 0 is modulus of B, determinant of B is equal to 0. Hence the condition for a non-trivial solution, determinant of A minus lambda I is equal to 0. So A is written in a matrix form, A11, A12, so on and so forth, A1n, A21, A22, so on and so forth, A2n, AN1, AN2, so on and so forth, ANn. And I will be G1, 0, 0, so on and so forth, 0, 0, 1, 0, so on and so forth, 0, so on and so forth. So you can write it explicitly in the form A minus lambda I. So that is nothing but A11 minus lambda. So lambda is subtracted in the diagonal elements. A11 minus lambda, A22 minus lambda, ANN minus lambda, and all other terms are remain as it. And this equation is called 2.5. This equation is called secular equation. Your A minus lambda is equal to 0 is called the secular equation or the characteristics equation of A. The evaluation of the determinant leads to A minus lambda I is equal to Cn lambda to the power n plus Cn minus 1 lambda to the power n minus 1, so on and so forth. C0 is equal to phi lambda. So your Cn are functions of elements of A, and phi is a polynomial of degree n in a lambda. So its n roots are eigenvalues of the matrix A. So you can evaluate those things, and your lambda 1, lambda 2, lambda 3, so on and so forth, lambda n is equal to A. That is product of eigenvalue of a matrix is equal to the determinant of the matrix. Then eigenvalues of a diagonal matrix you can see in the screen. You can have the corresponding secular equation and solve it. You have the eigenvalues lambda 1 is equal to A11, lambda 2 is equal to A22, and lambda n is equal to ANN. What are the properties of eigenvalues? A square matrix A and its transpose have the same eigenvalue. You can see the proof in the screen. The sum of eigenvalues of a matrix is equal to the trace of the matrix. Trace is the sum of the diagonal terms. You can see here. So there are some examples. Your lambda 1 plus lambda 2 plus so on so for lambda n is equal to trace A. That is the sum of diagonal terms. Here is an example so that the eigenvalue of a Hermitian matrix are real, and the eigenvector of a Hermitian matrix corresponding to different eigenvalues are orthogonal. So here is the proof. You can try this. There are some other examples. And there are also many examples in your course material. Then Cayley-Hamilton theorem. Cayley-Hamiltonian theorem states that matrix satisfies its characteristic equation. Every matrix satisfies its characteristic equation. If the characteristic equation of a matrix A, that is A minus lambda I, is equal to Cn lambda to the power n plus Cn minus 1 lambda to the power n minus 1 plus so on and so forth, C0 is equal to 0, then according to Cayley-Hamilton theorem, the matrix A satisfies the equation Cn a to the power n plus Cn minus 1 a to the power n minus 1 plus so on and so forth plus C0i is equal to 0. So you can prove it by taking the inverse of the matrix Q, which exists if the determinant is non-zero. So Q into Q inverse is equal to I. So Q multiplied by adjoint of Q divided by determinant of Q is equal to I. So your Q adjoint of Q is equal to determinant of Q multiplied by I. So your Q is equal to A minus lambda I, where A and I are matrices of the nth order and lambda is a scalar, you know. So A minus lambda I adjoint of A minus lambda I is equal to A minus lambda I multiplied by I. So A minus lambda I multiplied by B is equal to A minus lambda I multiplied by I, where B is equal to adjoint of A minus lambda I. So B can be written as lambda to the power n minus 1, B n minus 1 plus lambda to the power n minus 2, B n minus 2, so on and so forth, B plus B0. So by substituting these two in equation 2.24, that is A minus lambda I B is equal to A minus lambda I, you have A minus lambda I multiplied by lambda to the power n minus 1, B n minus 1 plus lambda to the power n minus 2, B n minus 2, so on and so forth, plus B0. So equating the like powers of lambda on both sides, your Cni is equal to minus B n minus 1. So you can see Cn minus 1 I is equal to A Bn minus 1 minus Bn minus 2, so on and so forth. And your Cn a to the power n plus n minus 1 a to the power n minus 1 plus n minus 2 a to the power n minus 2 plus so on and so forth, C1a plus C0i is equal to 0, which is nothing but the proof of Cayley-Hamilton theorem. Am I audible? Am I audible?
Yes, sir.
Okay. So there are many applications of Cayley-Hamilton theorem. One can determine the inverse of a non-singular matrix using Cayley-Hamilton theorem. The higher positive integral powers of it can be computed using Cayley-Hamilton theorem. And here are the examples. Cayley-Hamilton theorem can be verified for matrix A is equal to 1, 2, 3, 4, and you can use it to find A inverse. Okay. So you can verify Cayley-Hamilton theorem for the matrix A is equal to minus 1, 1, 1, 1, minus 1, 1, 2, 1, 2. And hence, you can determine A inverse, the inverse matrix. You can determine A inverse by using Cayley-Hamilton theorem. Okay, there
किस
are
ग्रुप में है
examples. ये आपका कोर्स मटेरियल में ज्यादातर चीज है और बाकी बड़े सारे किताब 4-5 किताब मिलाकर मैं किया हूँ. एक आपका है आर्फके नानू एवर, यू कैन गो थ्रू दिस. एक HK Das, you can go through that, Satya Prakash, and there are 2-3 more books. This is there in your course material in the reference section. So linear transformation, if X is equal to X dy, Y is equal to Cx dy, then R is equal to M. Yesterday I was discussing this. Then your similarity transformation, X is equal to Qx dash, Y is equal to Qy dash, and you have your A is equal to P inverse Bp, and this is nothing but similar transformation, and you will get similar matrix from it. Then diagonalization of a matrix. The theorem is like this. If a square matrix A of order n has n linearly independent eigenvectors, then A matrix P can be found such that P inverse AP is a diagonal matrix. And the proof is shown in the screen. Okay. So this is the preliminary idea from which you can have the detailed course material of your block 2. You can have it. So look, vector space, real vector space, you can define, let R be the set of all real numbers with its usual properties. So you can define it. A real vector space B is a set whose elements are called vectors and on which two operators are defined. One is addition of vector, another is multiplication of vector by a real number, you know it. Then element of vector space must satisfy condition of closure, commutative, associative, distributive, and successive multiplication of real number, these properties. And here are the proof. And here are some examples. I have discussed linearity, and here is the linear independence. Two non-zero vector u and v are called dependent on each other if one of them can be obtained by multiplying the other by a real number. So your u vector can be written as a multiplied by v vector. So they are called linearly independent. Linear subspace v1 is a subset of v is called subspace of v if all vectors in it satisfy the condition of a vector space. So we can call the set of non-zero vectors ui vector, u1 vector, u2 vector, so on so forth. Un vector is a basis and n is called dimension of the vector space V, and the vector space is having finite dimensional. And if the process does not stop, it has infinite dimension. In finite dimensional space, no matter how we choose the basis, the number of basis vector will always be the same. Then you can change the basis by using the component vector and the basis chosen thereof. Then your direct sum of vector space, if u1 is a subset of v and u2 is a subset of v, then you can write apart from zero vector, which must belong to every subspace, there is no other vector common between u1 and u2, and your v vector belongs to v can be uniquely written as sum of two vectors, u1 vector and u2 vector belong to u1 and u2 respectively. And your direct sum, yesterday I was discussing direct product, similarly you have the direct sum. Linear operators are mapping between vector spaces, and if v and w be two finite dimensional vector spaces of dimension n and m respectively, the mapping T such that v to w from v to w assigns every vector small v of capital V a vector, w vector which is T, which is a function of v of w in such a manner that every real number a T a v is equal to a T v. And the subspace K is called kernel of the linear mapping T, and your range of T in W is capital R. If the dimension of space B is n, dimension of kernel K, and dimension of range R, which is a subset of W, is R. So your n is equal to K plus R. Then product of operators, inner product or metric. So T square V vector is equal to T, TV and so on. And your inner product or metric is an additional structure on a vector space. An inner product or metric is an additional structure on a vector space, and the generalization of the dot product to an arbitrary vector space is called inner product. So it has three properties: symmetric, non-degenerate, and it is linear in the second argument. Then orthogonal vectors, it yields 0, and orthonormal, which will give you 1. Then orthonormal basis, the symmetry matrix contains all the information about the inner product, and we do not prove this statement here because it is not there in the course. And the basis is called an orthonormal basis, that is either 1 or plus 1 or minus 1. How can you construct orthogonal basis? It is shown in the screen by Gram-Schmidt process, Gram-Schmidt orthonormalization and orthogonalization, which I have discussed earlier in this class. Then signature of metric, the number T is called the signature of the metric. And for space-time in general relativity, G is equal to determinant of Gij. Then what is Hilbert space, which is often you can encounter in quantum mechanics. A complex vector space like the real vector space is a set of vectors which can be added to give another vector and which can be multiplied by a complex number in place of a real number to give another vector. So complex vector spaces occur in physics most prominently as Hilbert space, and complex vector spaces with a Hermitian inner product. So what is Hermitian inner product is shown in the screen. If H be a complex vector space with element F, G, H, etc., if your A, B, C, etc. be complex numbers, you can denote the zero vector by zero vector 0 over R arrow. Then for any vector small f, the multiplication by number 0 gives the zero vector, and any complex number C0 is equal to 0. So your A belongs to Hilbert space, or H and A plus zero vector is equal to F. And the Hermitian inner product on H associates to any two vectors F, where G belongs to H, a complex number denoted by F comma G, which has the following properties as shown in the screen. Then your Pythagoras theorem or Bessel's identity. So Pythagoras theorem states F plus G square is equal to F square plus G square, and your Bessel's inequality is nothing but F square greater than summation I is equal to 1 to n EIF to the power 2. This is Bessel's inequality. Square triangle inequality, and it is also called Cauchy-Schwarz Bunyakovsky inequality. This is nothing but F comma G is smaller than F multiplied by G, and it is explained in the screen. You can see. Then orthonormal basis. A complete orthonormal set is called orthonormal basis, and subspaces are called separate Hilbert space, and you can have it in your screen. Then your linear equations and matrices. You can see in the screen rectangular array of real and complex number is called matrix, which I've discussed in the previous class yesterday. You can see here inverse of a matrix, how you can get it. I have given you the methods, different methods, and some examples today. You can see here multiplication of matrix, addition, inner product, Kroneker's product, various types of matrix, unit matrix, all the diagonal terms are 1, null matrix, all the elements are 0, transpose of a matrix, yesterday I have discussed, or symmetric matrix, complex conjugate of a matrix, all the elements will be replaced by its complex conjugate, then the resultant matrix will be the complex conjugate of the original matrix, which is also known as Hermitian adjoint. Then inverse, orthogonal, and unitary matrices. Functions of matrix, matrix algebra. Yesterday I have discussed whether commutative or not, associative or not, elementary operations. Please mute yourself. Please mute yourself. Any question, if you have, then ask. Otherwise, mute yourself. Don't disturb other students, please. Then elementary operation, partitioning of matrices, which I have explained yesterday how it is arranged in different parts of a matrix. Yesterday I have shown you. Determinant, you know it in your higher secondary classes.
Finish.
Any question? Any doubt? Please ask.
Completed.
No completed. It will continue. Then eigenvalue equation, which I have discussed earlier today. There is an operator, there is an eigenfunction, and it will give you eigenvalue. And the equation is called eigenvalue equation, and you can have the trivial solution from its characteristics equation. then eigenvectors and eigenvalues. You see here the characteristic equation a minus lambda 1 is equal to 0, and the eigenvalues will be lambda is equal to 0, comma 2. This is evaluated from the characteristic equation. The diagonal values are written as 1 minus lambda because the diagonal elements are 1 in both the cases. So your 1 minus lambda square minus 1 is equal to 0. By solving it, you have your lambda is equal to 0, 2, which are the eigenvalues. So what is eigenvalue, anybody? In classical mechanics, you have deterministic things, specific values. If I ask the energy of a system, you can say it is 5 org or 17 joule or 120 org, like this. If I ask you what is the velocity of a particle, you can have a definite value, 5 meter per second or 17 kilometer per hour. If I ask you what is the position of a point, then you will have its position vector or coordinates in a Cartesian plane, Cartesian plane or three-dimensional plane, or a cylindrical or spherical polar coordinate system. But in quantum mechanics, the terminology is somehow different. It is not value, rather it is eigenvalue. If I ask you what is the energy of an electron, it has no meaning. I have to ask what is the eigenvalue of energy of that system. So eigenvalue of energy will give some meaning. The value of energy will give no meaning for an electron, a proton, or nucleon, or quantum mechanical particles, or photon, like this. So in classical mechanics, you have different equations, Newton's laws of motion, and other equations to evaluate value of a physical quantity, value of velocity, value of energy, value of force exerted upon a particle or exerted by a particle. But in quantum mechanics, you have eigenvalue of the energy of the of the electron in the fast orbit, eigenvalue of the energy of the electron in the third orbit in a hydrogen-like atom. So how can you evaluate it? By matrix algebra. So in matrix form, you have the operator, that is energy operator, E cap, which is operated upon the wave function psi, and you will have small e multiplied by psi. That small e is the eigenvalue of energy of that quantum mechanical particle. If you have your Hamiltonian H cap, when it will operated upon the wave function psi, it will give the eigenvalue Hamiltonian of that system. Similarly, potential V, whether when it is operated upon psi, it will give the eigenvalue of potential at that of that system or at that point. So this is eigenvalue of position, eigenvalue of momentum, eigenvalue of energy, so on and so forth. So this is very much useful in quantum mechanical systems. And in the screen, it is explained how you can get the eigenvalue from the eigenvector and the wave function. And from the characteristics equation. Am I audible? Am I audible? Am I audible? I think I am not audible.
Yes, sir, audible.
Yes, yes. You are. So next is inner product and orthonormal basis. So your U1 is equal to 1, 0, 0, U2 is equal to 0, 1, so on so forth 0, En is equal to 0, 0, so on so forth 1. And your X is equal to X1, X2, so on so forth Xn. So you can see the two orthogonal vectors are linearly independent and form an orthonormal basis. So you can have real orthogonal matrix like this. and consequence of that is the product of two orthogonal matrix is orthogonal. N column of S form of a set of orthonormal vectors, and matrix whose transpose its inverse is called orthogonal. And S transpose is orthogonal. The element of rows of S also form components of orthonormal vectors. Then your eigenvalues of an orthogonal matrix can be evaluated by using the characteristics equation and other methods. Here it is lambda is equal to +1 or -1. Then your real symmetric matrix A is equal to AB, BC, and it is real because quantity under the square root is positive. And you can see here from the characteristic equation you can evaluate lambda or eigenvalue. And here are some examples. You can go through this. Then moment of inertia matrix. Diagonalization of the real symmetric matrix, diagonalization by eliminating the elements in the rows and columns I have discussed earlier in this class. Hermitian and unitary matrix, Hermitian matrix and unitary matrix I have explained you to earlier in this class. A is equal to A dagger. Then Hermitian matrix A is a complex matrix which is equal to its Hermitian adjoint. Unitary matrix, you can see here orthonormal basis. And here are some examples and worked out problems. Then tensor, like vector, you have tensors, which is very much important in physics, and mathematical physics deals with it. So there are two tensors of rank 1. You have your contravariant and covariant vectors, and in contravariant vectors you can see V is equal to summation I V superscript I EI, and your in covariant vector you have your A sub linear function on the vector space B you can consider, and a linear function alpha defined on a vector space B assigns to each vector small v belongs to capital V a real number alpha. So here are an example. In 3 dimensions you can define a vector with the components x, y, and z. And in case of contravariant vector, you can see the component of the same vector in the other basis are related to the components in the first basis by the inverse transpose matrix, and the transformation of the components goes in the opposite direction than the basis. So this is why component of the vectors transform contravariantly, not covariantly. Then you can have contravariant tensor of rank 2 as shown in the screen. Just as second rank covariant tensors are bilinear functions of a pair of vectors d and w. A second rank contravariant vectors are bilinear functions of a pair of covariant vectors alpha and beta. You can have the inner product or metric tensor Gij is equal to Ei Ej. Higher rank tensors you can have higher rank tensors components transform similarity with a matrix S for each contravariant index and S to the power -1t for each contravariant index. Please mute yourself. You can see it in the screen. Please mute yourself. Then symmetry properties. Because of the tensor transformation formulas given in the general case, the components which are symmetric or antisymmetric in two indices also remain symmetric or antisymmetric in the indices in the same position. You can have the example T superscript ijk subscript lmn is equal to -T superscript jik subscript lmn. Then special tensor del ij and epsilon ijk, Kroneker's delta and epsilon. So Gij is equal to Eij. Matrices connecting two orthogonal bases must be orthogonal matrix. Okay. Then you have raising and lowering indices. Then you have raising and lowering indices. If a vector space has an inner product, then the metric tensor Gij and its counterpart G superscript Ij can be used for converting a contravariant vector into a covariant one or vice versa. In one case it is superscript, other case it is subscript. And you can convert one to another. Then contraction in a mixed tensor, that is a tensor whose components are both contravariant and covariant indices. If one contravariant index is set equal to one covariant index, then they are summed over the whole range, and we obtain a tensor with two indices less. And this process is called contraction. Are you getting it? Then your tensor product, bilinear function, and your tensor product. Yesterday I have discussed Kroneker's product, dual basis, dual space, vector and tensor fields. Vector field or a tensor field is concerned with an infinite number of vector space or tensor product of vector space. These spaces are situated at each point in space or in space and time. There are some examples you can work out: scalar fields and gradient fields and its components. Metric tensor field, here is an example. Trace tensor. Okay, so you can go through the self-assessment questions and prepare for the examination. Am I audible?
Sir.
I think. Okay, so this block is completed, block 2. Then we can have other parts. In block 4, you have your Fourier and Laplace transform. You can see in the screen. So this is very much important in electronics and some other field of application. So what is a Fourier transform? So you know Fourier series. It is very useful for periodic function, and by using complex exponential functions rather than sine and cosine functions, you may have studied earlier. And your complex Fourier series, you can discuss, or a function which has period capital T and a finite number of finite discontinuities in one period. This can be expanded in an infinite series of form. So this is Fourier series. Fx is equal to a0 plus summation n is equal to 1 to infinite an cosine of 2 pi. I think it is not visible, or is it visible?
Visible, sir.
Yes, okay. Thank you. So fx is equal to a0 summation n is equal to 1 to infinite an cosine of 2 pi nx divided by capital T plus bn sine 2 pi nx divided by capital T. So a0, n, abn are Fourier coefficients, and you can have complex Fourier series of a periodic function. Fx is equal to summation n is equal to minus infinite to infinite cn e to the power 2n pi ix by t, where cn is equal to 1 by t integration from minus t by 2 to plus t by 2 fx e to the power minus 2n pi ix divided by t dx, where n is any integer. So you have studied it in your honors classes, and this is just refreshing your memories. So now you can define Fourier transform, which is a new one, and some of you might have come across this in your mathematics, hardcore mathematics past course. So the powerful method of Fourier series is restricted to periodic function. Very often we come across situations in which we have to deal with aperiodic function, which is not periodic. consider a periodic function having a period t. So we now go on increasing the period so that it tends to infinite. The function will not repeat itself and will be aperiodic. You can see it in the figure 13.1. A is a rectangular periodic pulse and B is same pulse with a larger t. As t is made infinitely large, there is only one pulse giving an aperiodic function in figure C, 13.1c. So you can see periodic pulse of fixed width and height repeating with period capital T, and you can make the period capital T larger and larger and more larger to arrive at C, figure C. So fx is equal to limited. Please mute yourself. Please mute yourself. Fx is equal to limit t tends to infinite ft, which is a function of x. If the original periodic function contains a finite number of finite discontinuities in one period, the function obtained after taking the limit t tends to infinite would possess a finite number of finite discontinuities in the whole interval. Okay. So what should we do? We have to expand such aperiodic function. We can start from the complex Fourier series of a periodic function where t, the limit t tends to infinite. So your general periodic function ft with period t, you can write its complex Fourier series. So your kn is equal to 2n pi divided by capital T, and the complex Fourier series can be written as ft is equal to summation n is equal to minus infinite to infinite cn e to the power I kn x. So f subscript t x can be evaluated by substituting cn in the equation 13.14. So your 1 by t summation n is equal to minus infinite to infinite e to the power I kn x integration minus t by 2 to t by 2 fu e to the power minus I kn u du. U is the variable of integration. So your del k is equal to 2 pi by t, and you can replace 2 by t is equal to del k by pi. So your ftx is equal to 1 by 2 pi summation n is equal to minus infinite to infinite capital F, which is a function of kn multiplied by del k. So f kn is equal to integration minus t by 2 to t by 2 fu e to the power I kn x minus u du. So but three things might happen. The limit of all integral become minus infinite to plus infinite. 1 by t tends to 0, and the difference del k is equal to 2 pi by t between successive values of kn also becomes smaller and smaller. So we can deal the situation only if the integral minus infinite to infinite modulus of fx dx smaller than infinite, where fx is equal to limit t tends to infinite ftx. That is, the integral is finite. This is expressed by saying that the function fx is absolutely integrable. So, assuming that this condition is satisfied, you can now we can justify taking the limit t tends to infinite for ftx. So the left hand side can be replaced by fx, and by taking the limit t tends to infinite, the integral on the right hand side we can replace kn by k and the summation over n from minus infinite to infinite by integration over k from minus infinite to infinite. So these limits are consistent with the definition kn is equal to 2n pi by capital T, through which we can make the transformation from n to k. So you can write fk is equal to integration minus infinite to infinite fu e to the power ik x minus u d. So this can be rearranged as fx is equal to 1 by 2 pi integration minus infinite to infinite e to the power I k x dk integration minus infinite to infinite f, which is a function of u e to the power I k u d. So you can define gk as a 1 by 2 pi integration minus infinite to infinite f, which is a function of u e to the power minus I k u d, which is nothing but 1 by 2 pi integration minus infinite to infinite f, which is a function of x e to the power minus I k x dx. So your fx is equal to integration minus infinite to infinite g, which is a function of k e to the power I k x dk. So for region of symmetry, you can multiply both fx and gk by a term 1 by root over of 1 by root over of 2 pi, instead of having the factor 1 by 2 pi in only one function. So the Fourier transform is as follows: fx is equal to 1 by root over of 2 pi integration minus infinite to infinite gk e to the power I k dk, which is there in the equation 13.19c. And your gk can also be written as 1 by 2 pi integration minus infinite to infinite fx e to the power minus I k dx. So the first one is Fourier transform and second one is inverse Fourier transform. If a function fx possesses no more than finite number of finite discontinuities, and if the integral integration minus infinite to infinite fx dx is finite, then it can be expressed in form of an integral with the coefficient given in the inverse Fourier transform. What is the physical interpretation? The Fourier series of a periodic function tells us which frequencies or wave vector of a sinusoidal wave we should superimpose and what the amplitude of each wave should be, so that we get original function. So Fourier transform of a function tells us which wave or what frequencies and what amplitude should be combined to get the original aperiodic function. The only difference is that whereas it requires discrete frequencies, multiples of harmonics of the frequency of the periodic function to generate a periodic function. So we require a continuous range of frequencies to generate an aperiodic function. There are some examples. You can go through it. Then you know the Dirac delta function. Delta is equal to 0 when x is not equal to 0, and integration minus a to b del dx is equal to 1 where a comma b is greater than 0. Then similarly you can have your Laplace transform. Laplace transform are widely used in various areas of physics, especially in differential equations. So Laplace transform fs of a function ft is defined as follows: capital F, which is a function of s, is equal to integration 0 to infinite e to the power minus st f, which is a function of t dt. And Laplace transform of small f, which is a function of t, is capital F, which is a function of s. So you can write fs is equal to L ft, where L is an operator acting on the function f and giving rise to the Laplace transform. Similarly, you can have the inverse Laplace transform. Ft is equal to L inverse fs. So what are the properties? There are some basic properties of Laplace transform. One is linearity. Your L ft plus bgt is equal to af plus bg. Sign time shifting. L ft minus LFT minus T0 is equal to e to the power minus ST0 Fs. Frequency shifting, which is also known as fast shifting theorem, LFE to the power S0T is equal to F S minus S0. Time scaling, LF, which is a function of AT, is equal to 1 by modulus of A, F of S by A. Then time reversal, LF of minus T is equal to capital F, which is a function of S. Differentiation, integration, convolution, L, ft, equal to capital Fs, gs, modulation, L, ft cos omega 0 t is equal to half f s minus I omega 0 plus f s plus I omega 0. Similarly, the sine function, then initial value theorem, limit t tends to 0 plus ft is equal to limit s tends to infinite sfs. Final value theorem, limit t tends to 0 infinite ft is equal to limit s tends to 0 sfs. So these are all about Laplace transform, like that of Fourier transform. There are some worked out examples. So Laplace transform of elementary function c t to the power n e to the power ct cos pt sin pt cos hyperbolic pt sin hyperbolic pt is shown in the screen. You can have it. Then inverse Laplace transform. Inverse Laplace transform of the elementary function given in the table as shown in the screen, and your c is equal to 1. So inverse transform of 1 by s is 1, and that 1 by S minus C is equal to e to the power ct. So this is inverse transfer Laplace transform, and this can be found by reducing the given transform to the standard Laplace transforms of elementary functions. So there are some worked out examples. You can go through it. Then application. You can solve wave equation for amplitude of vibrations of an infinitely long varying string. That is del square y by del x square is equal to 1 by v square del square y by del t square wave equation. By assuming the initial condition y x comma 0 is equal to fx, you can solve it by Fourier transform. This shown in the screen. Similarly, the diffusion of certain quantity of salt in water, a diffusion equation can be solved by using Fourier transform, and this is the result. The concentration of salt in water at any time t, small, medium, and large. Then an infinite metal plate placed in the xy plane, as shown in figure 15.3. You can see here 15.2, 15.4, and this is 15.3. Okay. So the edge along the y-axis is maintained at temperature 0 degree, and the temperature in its edge along x-axis is given by T is equal to 100 degrees Celsius when x is between 0 to 1, and 0 degrees Celsius when x is greater than 1. Now the temperature of the plate satisfies the Laplace equation del square T by del x square plus del square T by del y square is equal to 0, and you can solve it by using the transform. Similarly, Laplace transform can be used to solve many problems like damped oscillator. You can see here damped oscillator, displacement of damped harmonic oscillator. You can solve it by Laplace transform. Laplace transform to solve initial value problem, y double dash 4y dash plus 3y is equal to 0. Y0 is equal to 3, y dash is equal to y dash at 0 is equal to 1. So this is the figure 15.7 for sin function ft, and you can solve it by using Laplace transform. Similarly, Newton's second law for impulsive force acting on a particular mass small a moving along a straight line is m d square x by dt square is equal to f of t, or f of t is equal to p del Dirac delta function delta t with p constant is an impulsive force acting for a very short time. So you can obtain xt from x0 and x dash 0. Electromagnetic wave equation E is equal to Ey or E is equal to Ez for a transverse wave propagating along x axis. Del square E by del x square minus 1 by v square del square E by del t square is equal to 0, or the initial condition E is equal to 0, and del E by del t at t is equal to 0 can be solved by using Laplace transform as shown in the screen. So here are some self-assessment questions and some worked out examples. You can go through it and you have an idea how it works. Then the next part is your partial differential equation and special functions. This is your block 1. I think it is there in the screen. So partial differential equation can be solved using separation of variable method, and Laplace equation can be solved in Cartesian coordinate, cylindrical coordinates, spherical polar coordinates, and it is independent of the coordinate system. Then there are many partial differential equations in physics, that is Poisson equation, heat diffusion equation, wave equation, Fredholm and Volterra equation. Then there are some special functions which can be solved, which are in the form of partial differential equation, and can be solved by using special technique. These are Bessel's function, spherical Bessel's function, your Hermite function, Laguri, Hormite, Laguri, vessel first kind, and storm Rivoli problem and other things will be discussed in this the course of discussion. So, I think in the next class we shall discuss the method of separation of variable and other techniques which are used to solve equations containing partial differential terms. So partial differential equation, one is separation of variable, and there are some special function for which we use special techniques to solve those. Am I audible? Am I
Yes, sir.
audible? So let us discuss it in the next class, or we shall continue. If you want to continue, then we can have it. We can have this discussion in the next class. This is up to you. So let us discuss it in the next class. Thank you.
Thank you, sir.